Okay, so I guess the two administrative things are that, yeah, I'll like listening to feedback and everything. I will try and review more homework 3 and homework 4 questions, and then also hold a final exam review session, like as separate from the sections, since we're not allowed to cover exam stuff in sections. But I don't think there's any rule about, yeah, review sessions. So cool.
Jeff,
Other than
I
that,
just have one question.
what'd you say?
I have one question. Are the midterms gonna be curved? Because we were like given a hint
I
that.
don't know anything about curves. I'm sorry. I don't know. They said TAs don't have any control over what's going to be curved or not. I've tried to say that a bunch of times. I don't know if I've said it here, but yeah, curve stuff you have to email Profs JR and Sperling. Sorry.
All right, thank you.
Yeah. All right, so I'm gonna go into the chat and paste the link. It should be sections. Oh wait. All right, I just pasted the link in the chat, and it should take you right to the slides. Or if it doesn't work, then here I will paste the GitHub. That should go to the GitHub that has like PDFs of the slides and everything. So cool. Share screen. 1 second, sorry. Cool. All right, hopefully you can see the slides. Yeah, this week we're doing hypothesis testing, and then correlation versus causation is like technically the unit, like the second unit of the week, but yeah, it's not really correlation versus causation so much as just understanding what correlation is and why it, yeah, it's the focus is on correlation and why it sort of, like the subtext is why it can't be used for causation, but I'm not really explicitly comparing causation and correlation. But the point is just that you should have it in the back of your head, like why the things that we're saying about correlation make it insufficient to establish causation. But anyway, that's like a really small, like 90% of the slides are about hypothesis testing. Yeah, so that stuff. Yeah, the like 2 bullet point summary of hypothesis testing is basically like the way that you test any theory, right, is like, well, I guess there's a bunch of ways to test theories, but the way that like the scientific method, the most effective way to test a theory under the scientific method is like statistical hypothesis testing, because the whole like mathematical branch of statistics was made to yeah, everything in statistics was created basically for this, right? To be able to take hypotheses about like, yeah, cholera or plant size, plant evolution, all the things that we learned in class, and like use the power of math, like the fact that you get deterministic answers and stuff like that, to figure out, yeah, to deal with uncertainty in the world, like the uncertainty of cholera. Like you don't know with 100% certainty that someone will or won't get cholera given some condition, or you don't know with 100% certainty like that a plant, you don't know what the plant's, like if you measure a bunch of stuff about a plant, you don't know necessarily what its offspring will look like, but you know like some statistical properties of it, like it will probably be around the mean, or it will regress towards the mean, like you learned in class. So the point is like to take general notions of hypotheses and like translate them into forms where you can use statistics to test them. It's just think of these 2 bullets. It's like, if the theory was true, what data would it generate, right? And now compare that to the actual data that you see, right? And again, it's not like deterministic. So you can't just be like, oh, well, these aren't the exact same, and therefore my theory is false. It doesn't, it's not that simple, right? It's, you wanna think about, okay, under my theory, the data would look like this, and this is what the data would actually look like. But now you kind of have to come up with like a number or like a, yeah, some sort of statistical procedure for measuring like how similar or how different these are, right? And then you can come up with thresholds, like p-value thresholds is what they use for like for scientific journals, right? Where they say, okay, like if they're similar enough, we will like, you know, or how do I put it? If they're different enough, then we can reject that, like the theory that you're proposing, right? If the theory you're proposing generates data that looks like this, and then the actual data is just completely different and looks nothing like the data that your theory would generate, then, you know, we can reject your theory, but we can never accept your theory. And that's because of just the problem of induction, which you can look on Wikipedia or something. Like, it's just the idea that you can always like go and get more data, or things might change in the universe tomorrow and we can't know. Oh yeah, I'm sorry. Yeah, TLDR means like if the slides are too long and you don't want to read them all, like this is the summary. Thanks, Julian. Yeah, it just means this is like the summary. Cool. So the example we'll be working with in this section is like, so say I walk up to you, right? And I say, hey, do you want to gamble? I have this, we'll each put in $1 and then I have this coin and we'll flip it. And if it's heads, I get both of our dollars. You know, I get my $1 back and I get your $1. And if it's tails, then you get both of the dollars. And so, but the thing is, right, like coins can be loaded, right? Like you can like scrape off certain, or you can put really heavy material on one side. Just, yeah, there was a professor where I went to school before, his name is Percy Diaconis, and he can like perfectly flip a coin so that it's heads 100% of the time, or tails 100% of the time. Like he trained himself to do that. So yeah, the point being like, but I mean, that's a little different because that's like his technique of flipping. But in this case, we're gonna think about like the coin. Like, do we trust that this coin is fair? Because if it's fair, then like, sure, that's a fair bet. You could just do it for fun if you wanted. If it's not fair, then it's just basically me stealing your money, right? Like if I've weighted it so that it almost always comes up heads, that means I'll almost always get the money, right? So that's not a good deal for you. So yeah, there's two DSUA111 students. One is Xavier and one is Yasmin. So Xavier says, okay, I trust Jeff. I think the coin is fair. I think heads and tails will come up about the same number of times on average, right? So that's Xavier's theory. Yasmin says, actually, I don't trust Jeff at all. I think that, yeah, he's weighted it, loaded the coin so that heads will come up more often than tails, right? And in response, I just say here, sure, I understand your concern that I just randomly walked up to you and offered you this bet. Here, I'll let you take my coin and flip it 100 times. Then you can draw your own conclusions about whether it's fair or not, right? So it's kind of like you have 100 coin flips to determine whether or not this is fair. And so in terms of, you know, going back to this TLDR, which is like, if your theory was true, what would the data look like? Now compare that to the actual data. So let's focus on the first bullet point, right? If your theory was true, what would the data look like? So in the case of Xavier's prediction, right, that the coin is fair, what the data would look like is you'd flip it 100 times and about 50 of them would be heads and 50 of them would be tails, right? Whereas Yasmin's prediction, it's a little uncertain, right? So we'll like talk about that later, but for now, let's just say, you know, we say, all right, Yasmin, like, but what's your prediction for the number of heads and the number of tails, right? And she says, okay, I think 75% of the time it'll come up heads, right? So it'll come up heads like 3 out of every 4 times. Yeah. On average, right? So it's not like, oh, the number of heads will be exactly 25 or whatever. It's like, I expect it to be around 25, whereas Xavier expects it to be around 50, right? And so this is just a function I made that says that creates a little graph so we can visually see what this looks like, right? And it's kind of dumb, but I just wanted you to get used to plots like this, right? So that you don't have to always think of it as like numbers, because this is kind of like, this makes people run away from math. And this,
Am I supposed to know how to create this function?
yeah, it's just I could have done plt.hist. It's just plt.bar. You can Google, it's matplotlib. Like we learned like how to do line plots and, oh, you're asking for like the exam? No, I don't make any of the questions on the exam. I don't know what's going to be on it. I'm just trying to teach data science. Like it's just a graph of I just Googled matplotlib bar plot, and then it came up like.
Okay, but you didn't define like Xavier and Yasmin. So how does the function know when you put in Yasmin then?
Oh, right. Yeah, that's a good question. So because I had 2 arguments here, right? One is the prediction and one is who's making it, right? And so this call, right, it plots the prediction that they make. And then when it makes the title, it just plugs in who. So this notation is like the same as if I put like who and then a plus sign and then quote apostrophe s coin flip prediction. This is just a shortcut. If you put f at the beginning of a string, then you can use this notation with like curly brackets. You don't have to learn it for this class, but it just seems more natural to me to put like whose coin flip prediction and then it plugs in whatever the argument was. Right?
Okay, got it.
So yeah, like we could like, the reason I make this function, right, is because technically you could have like 100 students and they could all make different predictions, and then you'd be able to use this to plot, like, because just showing like how to make a general, plotting function. So yeah, in this case, x predictions is the variable where I stored like the predicted the distribution that Xavier predicts, and then I gave the string Xavier and it plugs it in the title. Whereas for Yasmin, different distribution, right? Just showing you that, these numbers, when you do probabilities, like they're not just numbers like in algebra where you're just like solving for x. Like the numbers have a meaning in the sense that like, this isn't just like x. This is, oh, Xavier is predicting that heads will come up 0.5 proportion of the time. Cool. And then if this is also, you're not responsible for it. This is just like, I wrote up some functions here, like, so this one does, so I should say here, don't worry about a lot of this, but I'll show you what you need to worry about here maybe, is here I import secret _coin, and that's just because I made a Python file called secret_coin.py that just has like a function called flip, right? So you can do secret coin.flip. And I just did that because I didn't want it to show up in the slides whether the coin is weighted or not, right? Like you can go on the GitHub and you can look at it, but the point is like in these slides, putting it in a Python file outside and then importing it makes it so that like I can use the function .flip, but it doesn't show you the source code. It's not like secure. Like I said, you can just go on the GitHub and look at secretcoin.py, see whether it's loaded or not, right? But I just wanted to show you what it looks like, that you can import not only like matplotlib and pandas and numpy, but also like you can write your own functions, or you can write a library and then you can just import it, right? I called mine secretcoin. np.random.seed, so that is just seeding a random, so usually NumPy would like actually generate random numbers, but if you want it, like if you're teaching, right, and you want it to be the same for everyone, like I want the results to be the same if you run this code and if you know, Ibrahim runs this code and Julienne runs this code. So np.random.seed just says like, it seeds the random number generator with a number, in this case 1, 2, 3, and then all the random numbers that get generated after this are going to be the same sequence. So meaning like, if I run it on my computer, it will generate the same sequence of random numbers as if you ran it on your computer. Whereas if you didn't do this np.random.seed, what would happen is this gets called no matter what, and it just would use the time in milliseconds. So just so you know, like if two people run a random number generating algorithm at the same time, like exact same time to milliseconds, it'll generate the same sequence of random numbers because they're not actually random, they're pseudo random. Actual random numbers cost a lot of like money and computation power to generate. You don't have to worry about that. I was just showing you like what's happening here. So then now that I've imported secret coin, I can write this function do coin flips, right? It takes a single argument n and it just flips a coin that many times. You don't have to worry about it. It just calls secret coin.flip, does a little for loop. This is, yeah. You're not responsible for any of the contents of these. Just know that like they're functions, right? You recognize the def and then the function name, and then it takes parameters, right? And the similar thing with get flip distributions, you really don't have to worry about that. It just, what that does is it takes in like a sequence of flips, like 0, 1, 0, 0, 1, 0, where 0 is tails and 1 is heads. And just makes a little pandas data frame so that we can see, like we get like a table summarizing what happened with the flips. So you'll, in the next slide, you'll see it because I call do coin flips with 100, right? So it flips the secret coin 100 times, and this is the result. And then I just call get flip distributions, where I give it, here's what Xavier predicted, here's what Yasmin predicted, and here's the actual outcome. That's just this variable right here. Right? And it just makes a little table that like helps me a little bit because I can see, okay, outcome, tails. So let's read it right to left. So in the actual outcome, tails came up with probability 0.38, and in the actual outcome, heads came up with 0.62, right? Whereas Xavier predicted that tails would come up 0.5. Yasmin predicted tails would come up 0.25. So I only do this because you'll see like when we start generating plots, matplotlib is like simple enough that we didn't have to create like a pandas data frame to visualize anything in the previous slides. But Seaborn, which we've also learned or has been mentioned in lecture at least. Seaborn, like some of the Seaborn functions, you have to use a pandas data frame to like give it the information in a structured form. So we'll see, but what you need to worry about is like the theoretical thing here, like the statistics. So yeah, the actual observed flips, right? We actually carried out 100 coin flips by calling do coin flips function with n equals 100. And what we actually got was like, okay, tails came up, yeah, 0.39, so 39% of the time, as heads came up 61% of the time. Cool. But so we can say, okay, how wrong or right were Xavier's predictions or Yasmin's predictions, right? And this like question of like how wrong, how right is our theory, that's like the whole thing of statistical hypothesis testing, right? Because what we'll see here is like Yasmin and Xavier are meeting with each other and they're like, okay, who's right? Like, is Xavier more right? And it seems like fair. Like, should we believe Xavier's theory and do the gamble, right? Because it's a fair coin, or should we believe Yasmin's theory, right? And they're trying to figure out like, how do we say who was right and who was wrong? How do we say who made a good prediction and who made a bad prediction? So yeah, this is again not code that you're responsible for, just responsible for like knowing that you can make functions, because now you could just copy and paste this function if you wanted to do this on your own, right? That's like why I write them. Or when you're writing functions, you should be thinking about like other people using them, right? So in this case, like plot distributions, and I think of other people using them. Like if you make a table like this one here, and you pass it to the plot distributions function, it'll make a plot like this, right? I call it plot distributions A because I also made a plot distributions B function here. And the only difference is that in this case, it plots it by outcome. So it says like, okay, tails, the actual coin flip sequence, tails came up 39% of the time. Xavier's prediction was that it would come up 50% of the time. Yasmin's prediction is that it would come up 25% of the time, right? So maybe this is like a way to figure out how good or bad the predictions are. As we can see, like who got closer in the tails percentage, right? And here it's like a little hard to tell. It looks like Xavier is a little bit closer than Yasmin here. And then here, so the actual outcome is here, and like, yeah, Yasmin over predicted, but Xavier under predicted, right? So we run into like, this is not as simple as we maybe had hoped, because it's like, we can't just eyeball it. We can't just, in this case, we can't just look at it and say like, oh, Xavier's predictions are way better. I definitely believe Xavier or Yasmin, right? And another way to look at it is like, let's look at just heads, tails, right? But let's look at, here's the actual outcome, here's Xavier's prediction, here's Yasmin's prediction. So another, we could just say like, which one looks more like the actual outcome? And in this case, like, yeah, you might say, oh, Yasmin's prediction is better because it, you know, it predicted a gap between the number of heads and the number of tails, and there is a gap between the number of heads and the number of tails, whereas Xavier predicted there would be no gap, right? So the point of this is like, you're just going towards like, okay, this doesn't, we're kind of making it up as we go along so far. Like we don't actually know a statistically principled procedure for figuring out whose is better, right? We're just eyeballing these. But hopefully in your head, you're coming up with some ideas like, again, oh, maybe we'll say, you know, we'll look at the tail, the actual tails, and then we'll say like, we'll measure how badly they did by saying how far away they were from the actual percentage of tails, and same for heads, right? Or we could say like, how badly they did is how badly they predicted the gap. Like Xavier predicted a gap of 0, but it's definitely not 0. Whereas Yasmin predicted a gap of like, you know, 50, but it's also not that big. But so we're starting to think of like ways we could compare these predictions and see which was more right and which ones were more wrong, right? So yeah, let's just try it one more time, because the actual outcome looks like, you know, kind of sketchy, but that's only one trial. So we ask me again, and I say, yeah, sure, flip it 100 more times. Cool. You do 100 more coin flips. You make the chart again. But yeah, same thing, right? Yeah, we don't like have any good way of statistically like, you know, if you got a bunch of people in a room, you can imagine them arguing about this. Like they'd say, oh yeah, Xavier under predicted the gap, but Yasmin over predicted it, right? So anyway, all of this is just to say like, we need to formalize how to measure how good or bad a prediction is. And that's what statistics is, right? So we need a little bit of nomenclature, some buzzwords. In this case, the null hypothesis is the skeptical hypothesis, meaning there's no there's nothing out of the ordinary, let's say. That's a good way to describe null hypothesis here. So in this case, the coin is not weird, the coin is fine, it's like all other coins. Probability of heads is 0.5, probability of tails is 0.5, right? So that would be Xavier's prediction. Whereas the alternative hypothesis is just going to be the opposite, like it's the negation of the null hypothesis. In this case, it's like, no, the patterns are not just due to chance. They've actually, like of a fair coin, Jeff actually loaded the coin to be not even between heads and tails, right? So there the hypothesis is probability of heads is not, for this coin, is not 0.5, right? It's something else, like either heads comes up more often or tails comes up more often, right? But we just know it's not, or the alternative hypothesis posits that it's not 0.5. So that's Yasmin's prediction, right? And then What's weird is that there's only two possible conclusions we can come to from a hypothesis test that we're about to do, given these null and alternative hypotheses. So we can reject the null hypothesis if it seems sufficiently like sketchy, basically. So we're quantifying sketchiness, or we're quantifying how bad the alternative hypothesis prediction is, right? And if it's like, oh, actually the alternative hypothesis is like, we believe it more than we believe the null hypothesis, that they're even, that there's nothing weird about the coin, right? In that case, we can reject the null hypothesis that the coin is fair, but we don't accept the null hypothesis, because the point is, in science, you never prove anything, you only can disprove things, right? So you either disprove the null hypothesis or you don't disprove it, right? You never prove it. And we talked about that in the scientific method week. So yeah, it's like, the key thing is like, if it seems sufficiently unlikely that the patterns were produced due to chance. So we're getting like a little bit closer to numeric, or like quantifying our intuition about which predictions are good and bad, right? So we say, okay, I'm going to call one prediction the null hypothesis. I'm going to call another prediction the alternative hypothesis, right? The one that I call the null hypothesis should be the one where it's like nothing is out of the ordinary, basically. The null hypothesis should basically be our prior belief about the world. Like, oh, if you see a coin, you don't immediately think like, oh, I think that coin is loaded. I think that coin's going to be 83% heads, right? If you see a coin and you don't know anything about it, you haven't been able to flip it, you don't see anything weird about it, you just assume it's like a normal coin, right? So it should be like the conservative hypothesis, then a null hypothesis. But then if the data that is generated from the coin, right, like you pick it up and you flip it, or if it's an experiment, you go and you do the experiment and you analyze, you get a data set, right? You get the results. If the results are like, if the pattern in the results is strong enough that it doesn't seem like it was just produced due to random noise, then we can reject the null hypothesis. And that's where like we set a threshold, like I was saying before. In science, for better or for worse, mostly for worse, because it's a randomly chosen number, they set a threshold of like 0.05 for the p-value, right? And they say, okay, if the p-value is less than 0.05, that means that the data is so unlikely to have happened just by random noise, just by chance, that we think that the pattern that's posited in the hypothesis is not right. Like the null hypothesis is we reject that hypothesis in favor of the alternative. So what we need then, right, the thing I've been driving towards this whole time is it's a test statistic, which is a number that will tell us like, okay, it will help us detect whether our null hypothesis or our alternative hypothesis is, which one should we believe more, right? Or which one should we put more, if we had to gamble, right? That's why I did the gambling at the beginning. Like if you read like philosophy of statistics stuff, it kind of turns out that thinking of it like, would you take certain gambles? Would you take certain bets? That sort of turns out to be the best way to theorize a lot of stuff in statistics. So that's why I started with that. And the point is like, should we take the bet or not? Well, we come up with this test statistic and we use it to adjudicate, right? To figure out whether we should take the bet or not. Yeah, so it's a measure of how reasonable our alternative hypothesis is. So I think of it like a measure of weirdness, right? So it should get larger the more suspicious the data is, right? In the case of coin flipping, like if you get perfect 50-50, then you're not really suspicious, right? You're like, wow, I flipped it 100 times and I got exactly 50 heads and 50 tails. That's like the least suspicious outcome, right? Whereas like if you flip a coin 100 times and all 100 times it comes up heads, you should be really suspicious of that coin, right? And so in that second case, your test statistic should be really high. Your test statistic is like a barometer, like measuring weirdness. It's like a warning level. Like if the coins are 50-50, the test statistic should be 0. There should be no weirdness. There's no warning here. Whereas if it comes up heads 100% of the time, warning should be maximum. Your test statistic should be as high as possible. And for a sequence of dice rolls, right? If we did a similar gamble, but I had come up to you with a die, right, a 6-sided die instead of a coin, yeah, your test statistic should be low if you roll it 100 times and it comes up about 1/6, right? That's about 16. Like you get 1 16 times, you get 2 16 times, you get 3 16 times, and so on. That's the least weird thing because it's 1/6 of all the rolls are like on each face. But if you just get 6 every time, yeah, your test statistic should be really high, right? So my point is like test statistic is just a thing that we create, right? Or we don't have to create it from scratch. Like people have made test statistics for various like situations in the world, right? But the point is like we choose a test statistic. It's not like, oh, there is one test statistic that you have to compute. Like we choose it in a way that we think will best help us adjudicate between our null hypothesis and our alternative hypothesis, right? So for unfair coin detection, you could come up with a bunch of ideas, right? Like when we were looking at the charts before, I was saying, oh, maybe we could compare the, see who got better on guessing the number of tails, see who got better on guessing number of heads, or we could see who got the gap more right? The gap between heads and tails. So all of these things revolve around like, yeah, how we think the coin is fair if it's 50-50, right? And that means the number of heads is the same as the number of tails, right? And as it gets further from that 50-50, we get more and more worried, right? And so, yeah, this is the number that we were looking for before. It's not the only test statistic you could come up with, but it works for what we're trying to do, right? Which is that fair coins will produce a value when you compute this close to 0 on average, right? Sometimes the number of heads will be higher, slightly higher. Sometimes the number of tails will be slightly higher. But on average, if the coin is fair, right, and you say you just do it a ton of times and you compute this each time, like every 100 coin flips, you stop and you compute this value, it should be close to 0 for a fair coin, right? Whereas for a biased coin, it won't be 0. If the coin is biased towards heads, then it'll be like positive, right? Because on average, the number of heads will be more than the number of tails. Cool. So that's why it like works as a test statistic, right? We just say a coin flip outcome, the outcome of a bunch of coin flips is weird, is more weird as the gap between number of heads and number of tails increases.
Jeff, just one question. This idea, number of heads minus number of tails, will it be given by in the homeworks or exams? Will it be given by you, or do we have to like sort of make this ourselves? Will it say like, or determine what test statistic works best for this experiment?
Yeah, no, that's a good question. So the thing is like, in previous semesters, there have been some questions sometimes, rarely, but sometimes about like, oh, what would be a good test statistic to help us differentiate between these two theories. But I will say like most of the time, right, you're just doing like data analysis, like you're just getting some data set, like one that we've looked at so far. And there are like standard test statistics, right? Like if you Google test statistics, in fact, I'll just do it. Test statistic. And then you look at the Wikipedia article, there's just like a list of like standard test statistics. So like, yeah, let me wait for it to load. Yeah, see, so there's just all these like name of the test statistic and the formula for them. So all of these it's just like, these are standard types of statistical tests that people do, meaning like, these are generalized, like statisticians have identified like, oh, we don't have to make like a different test statistic for like coin flipping and dice rolling, or like 6-sided die rolling, 8-sided die rolling, 20-sided die rolling, right? Like there are general principles for what makes a good test statistic. And so I will say like, we could ask it like just so that you have intuition for what a test statistic is. right? Meaning, but over like hundreds of years of statistics, people have identified like these ones are just generally good ones for detecting, for example, like, you know, is our, like, there's a standardized null hypothesis and there's a standardized alternative hypothesis for a given type of test, right? Paired t-test, 2-sample pooled t-test, 1 proportion z-test, chi-squared test for variance, chi-squared test for goodness. Just there's all these different types of tests that are like standard to do on data sets for testing different things. Like for example, like paired t-test, that is like if you have data for where it's the same people that you're observing, but at 2 different time periods, let's say. So like you measure how much someone ate in 2020, each person ate in 2020 in calories or something, and then how much they ate in 2021. And you want to compare them, like they're paired, right? Meaning it's the same person, like it's Jeff 2020 and it's Jeff 2021. You might have a different situation where it's not paired, right? Where it's like, oh, I went into a school and I asked 100 people their calorie intake for 2020, and then I went to a totally different like school and I asked them their calorie intake in 2021. So they're no longer paired, like you don't see the same person twice. Then you would want to do like a 2-sample pool t-test. So that's what all these mean. They're just different types of data sets that you might get, and the test statistic that helps you see, like, say if the averages on some variable are different between 2 groups. So yeah, the point being, to finally answer your question, it's like, yeah, there may be a question that's like, oh, Sam is trying to make trying to figure out a test statistic for figuring out if this die is fair or something. Like what would that, and then ask you to write like a test statistic. But like more broadly in data science, and in this class, like we'll teach you the standard tests for things that you would want to test on a data set. So you're not making it up from scratch. You're just looking it up like on Wikipedia or in a textbook.
Okay, perfect. Thank you.
Yeah, no, that's a great question. Thank you. So let me go back to, cool. Yeah. Cool. And so now we have this test statistic, and we can say, well, how bad were our coin flip predictions? Well, it's a little weird because even with this test statistic, we still have to come up with like, what's it called? Statistically principled ways of comparing the test statistic from a fair coin with the test statistic from the secret coin, right? Meaning like what we can do is, yeah, here's the test that I just count the number of heads. You don't have to worry about that line. Count the number of tails, meaning you don't have to worry about this thing here. And then I just return number of heads minus number of tails, right? For a series of coin flips. And what all this line here is, I know it's like a lot of stuff nested, but it's saying, okay, 100, that's the innermost thing. Remember I was talking about nesting functions and how you want to read it from the inside out. So 100 goes into do coin flips, meaning it does 100 coin flips. Do coin flips, remember, flips the secret coin where we don't know whether it's loaded or not. And then it computes our test statistic from those 100 coin flips, and then it just prints the test statistic. So we do one series of 100 coin flips and we get a test statistic of 24, right? And what that means is that there are 24 more heads than tails. Kind of sketchy, right? We do another one, right? We call do coin flips 100 again, compute the test statistic again, and print it. And this time we get 26. So there's 26 more heads than tails. Even more sketchy. And now the key is like we say, okay, but how do I know what's 24, 26? Is that bad? Well, this goes back to the very first slide where you take the theory and you see what the data would look like if the theory was true, right? In this case, what would the sequence look like if the coin was actually fair, right? Before we were just saying, oh, it'll be something like 50-50, but now we can like really quantify it because we can actually just do fair coin flips, right? Like Yasmin and Xavier, they just take a coin out of their pocket and they know that it's fair because they just got it from like the treasury and they just flip it 100 times, right? And what they can do is they can say, okay, I'm going to flip fair coins 100 times and I'm going to compute my test statistic for that, right? And I'm going to see like, oh, okay, so is the test statistic for Jeff's coin like show more sketchiness on compared to the test statistics that would get generated from a fair coin, right? So meaning like what we see here, right, is that these are pretty high, like meaning these are above 20. They're 24 more heads than tails, or 26 more heads than tails. These are much closer to 0, right? And remember, 0 is our like least sketchy thing, right? 0 is what we expect. So in this case, though, again, because of randomness, right? When you flip 100 coins, you're almost never going to get exactly 50 heads and exactly 50 tails. In this case, we got 12 fewer heads, right? So we got 12 more tails than heads. In this case, we got 8 more heads than tails, right? But the point is, now we have this like procedure. We can take a fair coin, we can flip it a bunch of times, right? And we can compute test statistics to see what test statistics would look like for a fair coin. And then we can compare the test statistic that we actually observed from Jeff's coin, right? And see how sketchy it looks. So yeah, we'll just to like get a few more terms down, we consider a trial to be a sequence of 100 coin flips. You can perform 1,000 trials with a fair coin, right? With the fair coin, we can do it as much as we want. In this case, like since we're kind of doing this as an analogy for data collection and data science in general, you can think of it like it's costly to go out and obtain like more samples of the secret coin, right? Because the secret coin in the case of like a survey is like you have to go out and you have to pay people to take like an hour of their time to like fill out a survey, right? So you have to pay like 100 people $10 each or something. So it's like costly. So what we want is like a procedure where we can flip, we can take our expectation. Like we can say like, oh, I think that people will on average be, they'll like apples and bananas the same, right? Say that's what our survey asks. It asks like, oh, do you like apples more or bananas more? And our guess is that apples and bananas will come up the same, but we can just generate like null hypothesis that they're the same. We can just like simulate it, right? We can just say, okay, let me do a survey. Let me do like a fake survey where I just generate a random number, and that determines whether a simulated person likes apples or bananas, right? And I can compute the test statistic for that as many times as I want. The thing that's costly is going out and getting the actual data from real people, and then computing the test statistic from that data and comparing it with our null hypothesis. It'll make more sense when we see the graph here, because the point is, I just do a for loop, right? I start with an empty list. It says test stats, but it just is an empty list. And then what I do is I do same thing we did before. I call fair coin flips 100 to do 100 coin flips. I compute the test statistic for that sequence of 100 coin flips. And then I just add it to test stats, right? Test stats.append just says put it at the end of the list, add it to the end of the list. So in this case, I do 1,000 of those, right? I just do for trial num in range 1,000. And note that I don't actually use the trial number. So like trial num just gets thrown away. But it's just in case you did want to like check your code, it's good to do this, because then you like if something's going wrong, you can like print out what trial num is and be like, oh, something weird happened on trial number 300 or something. Anyway, I do 1,000 trials of 100 coin flips, right? This line gets run 1,000 times. So I have 1,000 test statistics. And what that gives me is a distribution of test statistics, right? I just do plt.hist of the test statistic. And wow, it looks like a normal distribution that we learned, but the key here, right, is that now we want to say, okay, so most of the time, yeah, good. For a fair coin, most of the time the test statistic is 0. You know, sometimes it's higher, like this is like so let's say, yeah, things over here represent like 10 more heads and tails, 20 more heads and tails, right? So even with a totally fair coin, sometimes you get like 30 more heads and tails. Really rare, right? Like 1 in 1,000, but it's happened sometimes. And sometimes you get like 35 fewer heads than tails, right? But it's just really rare. And that's what I'm talking about with like random noise. Like it's not just, oh, every single time I get 50 heads and 50 tails, right? Sometimes it's higher, sometimes it's lower, but this is the distribution of what the test statistic will look like under the null hypothesis of a fair coin. The reason we make that plot is because now we can compute our test statistic for the actual like Jeff's coin flip, right? So I take Jeff's coin, remember it's like costly because if I flip it too many times, he'll say, I don't like that you're testing it so much. I don't like, you know, too much statistics. I don't like this bet anymore and I'm going to leave. But so we just say, oh, can we just flip it one more series of 100 times? And I say, cool. And we compute the test statistic from that and it's 8. So Jeff's coin produced heads 8 more times than tails out of 100 coin flips. And we plot that, right? So I put a little red line of where that lies. And it's like, it's hard to tell, like that it is higher than, you know, the average, but it's not so much higher that it couldn't have been produced by chance, right? Even when we flipped a fair coin, like 250 times out of 1,000, we got a test statistic around that, right? So 8 is not like a very extreme test statistic. So from that, we might think like, oh, it's actually, I think it's fair, right? We might make a cutoff at like, oh, it's actually like very likely that you could get a test statistic of 8 even with a fair coin, right? And that's what a p-value is. A p-value is just what's the probability of getting a value this extreme of your test statistic if the null hypothesis was true, right? So in this case, if the coin was fair, which is what this distribution is, what's the probability that I'd get test statistic of 8 or higher, right? That the heads minus tails gap would be 8 or higher. And the point is it's like pretty high. So like 25% of the time, right? 25% of all the fair coin flip trials, the test statistic was 8 or higher. So it's like not unlikely that it could be generated by chance, right? If you're submitting to a scientific journal, they'd say, oh, that p-value has to be less than 0.05 for us to think it's like, oh, that's a really extreme test statistic, right? But let's increase the sample size because watch what happens here, right? This is like the danger of like when people are like, oh, don't believe that study, it only asked like 20 people. This is why, because that was a sample of size 100, right? I'm flipping 100 coins each trial, but let's just increase it like a little bit, like to like 500 coin flips per trial, right? So this time it's the exact same code from before, but I flip 500 coins in every trial. I do 1,000 trials, each of which is 500 coin flips. And then I still compute my test statistic, right? But now it's like number of heads out of 500 flips minus number of tails out of 500 flips, right? So it's like a little more sensitive and it looks pretty similar, the null hypothesis distribution, right? But now when we flip my coin 500 times, now this is where it starts to look sketchy, right? We go, wait a minute, we flipped it 500 times and we got 88 more heads than tails. And that never happened ever when we flipped our fair coin, right? When we flipped our fair coin, the most extreme was like 66 more heads than tails or 76 fewer heads than tails, right? We never got a number as extreme as 88. So the whole point of like that lesson is basically that if your sample size is too small, you won't be able to you won't have enough, it's called statistical power. Like you won't have enough statistical power to detect whether it's fair or not, right? Because now we compute our p-value and it's just 0, right? None of the fair coin flips trials, none of the trials of 500 flips of the fair coin produced a test statistic as high as the test statistic we just got from the secret coin, right? So yeah, that's 0, and scientific journals would say, oh, that's a really like something is wrong. Like I think we can reject the null hypothesis that it's a fair coin, right? Because it's so unlikely that a fair coin would produce 88 more heads than tails out of 500 flips, right? Cool. And the rest is just kind of like auxiliary because he's just showing you that you can have different test statistics. So in this case, I just take the number of heads minus the number of tails and I square it. Actually, let me make sure I drive this point home. Yeah, so hopefully that makes sense. We increased the sample size and that allowed us to detect, oh, and the moral of the story is that it's not a fair coin. You can go into the GitHub and you can look at secretcoin.py and yeah, it was set so that it would come up heads 60% of the time and tails 40% of the time on average. So it's a biased coin towards heads. Yeah, now you know. But we detect it, right? We didn't detect it with a sample size of 100. Because with a sample size of 100, we got a result from flipping that biased. Now we know it's a biased coin. And it was like, yeah, I got more heads and tails, but it wasn't so out of the ordinary for 100 flips. But when we did it 500 flips, yeah, we got a result that was very out of the ordinary and probably wouldn't be generated by a fair coin. Cool. Yeah, these are just alternative test statistics. Same idea, right? I just have this different test statistic where I square the difference in heads and tails for fun, and then I just plot it. And it's a bad test statistic, right? It's like less good because now the coin that we now know is biased. Now it looks really like not, it looks really normal, right? We say, oh, that looks right on target, right? That this flip looks like it, this flip of the secret coin looks like it fits perfectly in the distribution of test statistics for the fair coin. So we just say, oh yeah, it's definitely fair from this, right? So this is not as good of a test statistic. It's like has less statistical power for detecting biased coins. And then this one's even worse. This one is just like, if the difference between heads and tails is less than 5, then we say it's 1. Otherwise it's 0. That's it's no good. It's just showing that like these are all valid test statistics. They're just really bad for detecting whether the coin is biased or not. Yeah. And so it just comes into, this is the last thing I'll do. I'll do correlation next time because I see that we're over time. But the normal distribution, just all you need to know about it really is that like it's a certain shape of a distribution that has nice properties in terms of like, we know exactly what percentage of all the values fall between 2 standard deviations, what percentage of all the values fall between 3 standard deviations of the mean of the data set. And so in this case, last thing, I'm plotting, this is the same test statistic distribution that we plotted before, right? It's test stats 500, but now I've normalized it, which we learned in class, where I subtract the mean and I divided the standard deviation. And so now the x-axis, it isn't the number of heads or tails, it's actually the number of standard deviations away from the average number of heads or tails, from the average test statistic value. So if a trial had exactly the average test statistic value, it now has 0, right? But if it had 1 standard deviation higher than the average test statistic value, now it has value 1 when I compute these z-scores, right? And what the last thing that you need to know is like, okay, wait, so this looks normal, but like, again, that's just intuition. That's just looking at a picture. And it's like, how do we actually know that it's normal, right? Well, that's why I brought up the property about like, oh, this percentage of the values are between these 2 points on the distribution. We can actually compute that. So I just did another function. All it does is it takes in z-scores and it says how normal they are, because what it does is it just says, okay, the percentage. So in this case, I give it the test stat z-scores. I give it this data set, and it's going to tell me kind of how normal it is by saying, okay, percentage within 1 standard deviation. It should be 68.5 is like the official thing for a perfect normal distribution. Like in a perfect normal distribution, 68.5 of the values will be within 1 standard deviation of the mean. In this case, it's 69.7, let's say. So it's a little bit higher. But then the percentage within 2 standard deviations, 95.1. It should be 95.0. So again, it's like very, very close to normal, but it's slightly not. And then percent within 3 standard deviations, this should be like 99.9, but it's 99.7. So the point is like these numbers here, these are like almost like a test of how normal your distribution is, right? So you can take any distribution, you can plug it into this function, and it just figures out, it just says, okay, let me take the whole data set, find the mean, and then compute how many of the values are within 1 standard deviation of that mean, right? And perfectly normal distribution would be 68.5, 95, and 99.9, sorry. And we see, so it's like, it's pretty close to normal, right? But it doesn't have to be that way. So here's the test statistic B, the other test statistic that I made. Here it's like not at all, right? The percentage within 1 standard deviation is already 91.2. Right, and that's just because the mean is somewhere like around 0, and then like most of the values are also down around 0. So yeah, the percentage within 1 standard deviation is like already 90%, right? Whereas for a normal distribution, it would be 68%. So it's just showing you that like this 68%, this like 68, 95, 99.5 rule, I think it's called. That's just for normal distributions. It's not like all distributions have like, oh, one standard deviation is 68.5% of the data. It's like, that's only for a normal distribution. And I just say that because on like an exam or something, you might get a thing that says like, oh, John performs an experiment and finds that the mean height is 150 centimeters, and the standard deviation of that height is 10 centimeters. And then it'll be like, what can John say about the data? And it'll be like, one of the options will be like, oh, 68.5% of the people are between 140 centimeters and 160 centimeters. That's not true, right? Because that's only true if we know that height, the distribution of heights is normal, right? It might not be. It might look like this non-normal distribution. So cool. I just wanted to drive that home.
65%, 95%, and 99.9%.
Yeah, it's like that. You know, I don't think it's important to know the exact numbers, but yeah, it's like 68, 95, 99 rule.
Okay.
Here, Wikipedia, 68, 95, 99.7 rule, right? Which just says, yeah, for a normal distribution, about 68% of all the data points will be within one standard deviation, about 95% will be within 2 standard deviations of the mean, and about 99.7% of all the data will be within 3 standard deviations of the mean, if it's normally distributed. Again, all this gets thrown out if it's not a normal distribution. Cool. So I'm going to stop the recording and then, yeah.
I just have a quick question.